There we are. Oh.
Okay, I'd like to thank the organizers for giving me the opportunity to share about what we think is happening in superconductivity in magic twisted bilayer graphene. So this work is done in collaboration with Namin, Wei-Ching, and Alan, and they are from UT Austin. It's not fair to assume everyone is very familiar with Moiré materials, so I'm just going to spend a minute to get you excited about this platform of this strongly interacting platform that arise from two-dimensional materials. So what you see here is really just two layers of graphene, and you twist them at a given angle. And if you do that, the unit cell suddenly becomes 1,000 times larger than the fundamental unit cell. The magic really happens when you put in electrons one by one into these 1,000 atoms unit cell. Okay, and the way we measure the amount of electrons inside this Moiré unit cell is with this number nu, which we call filling factor. It's nothing but electron density times the Moiré unit cell. And in 2D materials, you can really control the electron densities on the order of 10 to the power 12 per centimeter square by gatings. Okay, so let's see what happens. So if you start from neutrality, nu equal to 0, you have a slightly resistive state, nothing really interesting. But if you just add in one more electron, okay, so you get a resistive state, and you have a very large Hall resistance. Okay, this is what we call a correlated chain insulator. So if you just add in one more electron into this 1,000 atom unit cell, you completely change the property. You become a very strongly correlated insulator, and with no Hall resistance. Okay, just to remind you, according to band theory, at 1 to 3 filling factor, you should just get a matter. So the fact that you see all these interesting resistors and anomalous Hall insulator is really telling you interactions are playing a very important role, and you can break you can break time reversal symmetry in the orbital sense just by interactions. So arguably, the most interesting part of this phase diagram is this thing, superconductivity that occurs between -2 and -3 filling factors. So these are whole dope filling factors, meaning we remove 2 electrons into these 1,000 from this 1,000 atom unit cell, and typically the whole dope superconductor is stronger than the electron dope superconductors. So this type of phase diagram has been routinely seen by many experimental groups around the world. I chose this data from Dmitry Yefato's group because it shows both quantum anomalous Hall insulator and superconductor in the same sample. Okay, but it has also been seen in many other groups, as I said, notably the one by MIT where they first discovered in 2018. Okay, so the main message today is I'd like to present a theory, microscopic theory of superconductivity for this system. Okay, so the pairing channel is a spin triplet and valley singlet, and the glue that gives rise to superconductivity is due to what I call a sublattice paramagnons. So it's what gives rise to this dome, and in the experiment we have some evidence that from Hall density data, STM data, penetration field capacitance data, that around nu equals to -2, you have very small density of states. And as you increase electron density, have a larger Fermi surface, and the density of states increases. So the fact that superconductivity disappears when you increase the Fermi frequency of states requires an explanation. And that's my third message. That is, you have, when you approach -3, you're approaching a valley polarization instability, and this gives rise to a valley paramagnon and suppress the superconductivity. So, so my job today is to convince you, because our theory explains certain feature of the experiment, it cannot be too terribly wrong. So let me just start to remind everyone, what's going on in this Moiré material. So what you see here is a Moiré superlattice, and I've drawn the Moiré lattice vector for UAM. So what Alan and Rafi Bistritzer did about 10 years ago is to say, okay, I want to find a set of bands that satisfies this unitary eigenvalue problem, this block condition. And so what it means is when you translate the 4 electrons by a Moiré unit cell, all of them pick up exactly the same phase, the block phase. So they say, what is the minimum model to understand the dispersion of these block bands? So these are well-defined solid state problem. And what they found is when you twist them at a certain angle, at about 1.05, the spectrum of this periodic Hamiltonian suddenly collapse very close to zero energy. Okay, and at that time, they don't know why this is so, and they call these the magic angles. And so this type of magic angle realized the strongly correlated state platform that Chimel told us yesterday, where the Coulomb interaction is much bigger than the bandwidth. Okay, so it turns out a few years ago, Gregory Tarnopolsky and collaborators found that if you tune the Moiré potential to a condition where you change, when the Hamiltonian changes sign, when you flip sublattice, unfortunately we call it a chiral limit in our community. So if you go to this chiral limit at the magic angle, all these bands become completely flat. And the zero energies become doubly degenerate, all of them. So you have two n degenerate zero energy states. So that explains sort of why there's a complete flat bands at zero energy. So you should think about these flat bands of having 8 degrees of freedom. So at h momentum k, you can think of it having sublattice, which is a well-defined quantum number only in the so-called chiral limit. And you have tau, which is because you have electrons from 2-value in graphene, and you have spin. So this 8-dimensional octet pseudospin object is what I'm going to call a pseudospin.
Can I ask the
Sure.
by your notation, the upper right, 1, 2 refers to the 2 layers? Or?
Yes. Mm-hmm. So we have a flat band, and first thing we can ask is what happened when you have electron interaction in these bands. So we know from quantum Hall effect, if you don't have any kinetic energy, and you put in, you half fill the Landau levels, and you can write down the many-body wave functions exactly. So this is a many-body wave function. The coordinate and spin of the first electron, coordinate and spin of the second electron. It turns out all the spin likes to align together to have a maximal spin polarized state. Because when you do that, the electron coordinate have to be anti-symmetric, all of them, and this lowers the exchange energy. And it turns out if your Hilbert space is projected only to lowest Landau level, this is an exact eigenstate at half filling, because it has all the exchange energy and you don't have any phase space for quantum fluctuations within the lowest Landau level Hilbert space. So, and this is what we call quantum Hall ferromagnetism, basically. So, So can the similar ideas appear in measure angle to bilayer graphene? And indeed, it does. So this is a result from our group in Austin. So this is a self-consistent Hartree-Fock mean field calculation. When you just fill in at filling factor -3, you fill in 1 electron into these bands. So in valley K, you have 4 bands, and in valley K prime, you have 4 bands. Each blue and red in the valley K prime are doubly spin degenerate. Okay, so if you forget about all the magnetic anisotropic, let's say from spin orbit coupling or intervalley scattering, then by the same argument as a quantum Hall ferromagnet, we indeed find that the system was spontaneously polarized into a given flavors. So you have 8 flavors and you spontaneously polarize into one of them. And you can, by that, and it happens that this band that you occupied, the lowest blue band in the valley K, happen to be Chern band, because you completely occupy them. When you use the TKNN formula, each of the occupation number is 1 in this band, so you get a quantized anomalous Hall effect. Yes.
You have actual symmetry for the pseudospin, or what is this?
So you have SU2, depends on the model. So typically you have SU2 spin rotation in one valley and SU2 spin rotation in the other valley. But but you could always enhance the symmetry by dropping off certain terms. But the minimum order that you like to think about is just SU2 cross SU2. And okay, so and this is indeed the quantum anomalous Hall effect that is seen by this is the data from Andreas' group, but it has also been seen by David Goldhaber-Gordon's group in Stanford. You see this is a Hall resistance, and it jumps, and there's some noise in jumping, and that has to do with the domain walls. And in this paper, they've shown how they can clean and sweep the domain wall with magnetic field and also with current. There are some tiny details about boron nitride alignment, which I will not go into details. But okay, I don't think I have much time, but so that's just one extreme limit of quantum Hall of magnetism in measure angle twisted bilayer graphene. Thank you. Okay, much better. So this is sort of a Fermi surface reconstruction, and you can see there's certain jump in Hall density. This is Hall resistance, Wakefield Hall resistance, and this jump is also an indication that there is exchange effect playing roles in these materials. I can discuss these later if you guys are interested, but let me move on to conductivity, okay? So the first two the slides just now was just to show you that magnetisms are pretty much everywhere in the phase diagram of measure angle twisted bilayer graphene in the pseudospin sense, okay? So now let me just build on what Professor James told us today in the morning about helium, okay? So Professor James told us that there are 2 parameters that characterize the interaction strength: the symmetric in spin, the anti-symmetric in spin. So this gamma up is what I'm going to call is a spin symmetric plus a spin anti-symmetric. Gamma up down is a spin symmetric minus the spin anti-symmetric. So this just means this is the interaction between 2 helium atoms with the same spin. And this is Coulomb interaction between 2 electrons of opposite spin. In the normal liquid phase, they're only parameterized by these parameters. So what I'm plotting here, this is attractive, okay, and this is repulsive. Okay, so I'm going to only focus on that phase diagram, what so-called phase diagram, theoretical phase diagram, when the opposite spin is always repulsive. So typically, before 1972, when we found superfluid in helium-3, theories typically start somewhere around this part, and they try very hard to find when the condition, it will change sign if you superfluidity. So what Anderson and Brinkman did was to say, hey, let's do something simpler. Let us start from this point, and this is what they call the Paramagnon model. In the Paramagnon model, you don't have any bare interaction between like spin. And that's because the exchange effect is so strong, it directly cancels out all the direct interaction. So if you start from this point, okay, and you crank up your partition theory, at first order, you have to scatter with opposite spin in order to come back to the same spin. So at first order, you're going to go here. Okay, at second order, you'll put two bubbles into the effective interaction, you'll go up. And then if you go up like this. So the end result is you create a sort of right, let me just run all this. So you create a repulsion in the singlet channel, and I'm going to call this the Berg-Schrieffer repulsion because it was first discussed by Berg and Schrieffer to explain why in certain transition matters where you have strong electron-phonon coupling, but you don't see superconductivity. For example, close to palladium, there's no superconductivity. And that's because there's a strong singular repulsion they'll break singlet pairs. And I'm going to call this thing the Anderson-Brinkman triplet attraction. Okay, so the reason why is from this bare interaction, and if you sum up the ladder diagrams, you move the system somewhere to this point. So you can think of this moving in phase space as increasing the pressure, and if you know when you increase the pressure, you bring the system to the border of a more insulated of a solid phase close to the melting curve, where the spin susceptibility enhances by a factor of 25, right? So this is the paramagnon peak. They start to accumulate at low frequencies, and this is what gives rise to superconductivity. Superfluidity, I'm sorry. So, okay, now back to measure angle twisted bilayer graphene. We have 8 degrees of freedom in spin in the pseudospin subspace. We're going to assume the spin is a ferromagnet. It's completely polarized. And so you are left with sublattice and valley degrees of freedom. So it's a sublattice and valley paramagnet. Okay, so we are going to study fluctuations. We are going to study a valley triplet channels. So Cooper pairs are drawn from opposite valley, 3 and 4, and they're related by time reversal symmetry. And so you have to consider 2 classes of diagrams. One is this class where you see electrons free coming in, you scatter, and then you create a particle hole pair, and the particle and hole actually lives in the same valley. So this is what we call density fluctuation, because the particle and holes are from the same valley. In this type of Berg-Schrieffer diagram, the particle and hole are from opposite valley. You can see 3 and 1 are from opposite valley, right? So tau and minus tau labels the valley. It's a heavy slide, and we do sort of a generalized RPA equation that account for both direct interaction, exchange interaction. And after all this analysis, we found the following phase diagram. Okay, so this is the just like helium. So this is just 2 Coulomb matrix elements. Okay, AA means is scattering between electron AA. All these are happening in a spin polarized Hilbert space. Just forget about spin. And they are drawn from opposite valley because of time reversal symmetry. And you also draw electrons from opposite valley, but now 1 electron, they are from opposite sublattice. So this is the y-axis. So first thing you have to realize is this looks terribly similar to helium in the sense, it doesn't matter how repulsive gamma AB is, the TC is always the same. Okay, so this is this color plot is obtained by, choosing your Bischofson-McDonald model, certain filling minus 2.4, 2.3, doesn't quite matter. And you add in attractive interaction gamma A and solve the linearized gap equation, and you get this. Got it. So, okay. And so our starting point, unlike Anderson and Brinkman, we cannot start from here, right, where gamma A is 0, because we don't have a Pauli exclusion principle to prohibit repulsion between electrons from opposite value, even though they're on the same sublattice. So we have to start somewhere here, and this difference, so gamma AB is more repulsive than gamma AA. It's this small difference is enough to lead to superconductivity when the system is very close to a sublattice polarization. And there are a lot of evidence in this graphene materials, as Jeannie can probably tell us later, in bilayer graphene, trilayer graphene, tetragonal layer graphene, the sublattice always like to polarize in order to lower the energy, because they always touch at a given point, at a Dirac point, and you go to bilayer, the density of states at the Dirac point become bigger, trilayer become bigger, so on and so forth. So interaction always like to break the degeneracies happen at the zone boundary, at the zone corner. So, and we think this is more or less, this should be true as well in twisted bilayer graphene. And there are experimental evidences that this indeed happened, that the system is on the verge of being sublattice polarized. So if that's the case, the system can move to this phase boundary and just basically at low enough temperature, it will become a superconductor. Now, the other part of the story, so this is what I'm going to call Anderson-Brinkman attractions, okay? So the other part of the story is why does superconductivity disappears when you move to -3, where we know the density stays increasing, okay? And the other part, and this is provided by Berg-Schrieffer repulsion, okay? Because these electrons are from opposite value, okay? And we know when you approach -3, the system like to be polarized in a given value. So there's a strong repulsion to push electrons when they from opposite values. And this is why when you approach -3, the system stop becoming a superconductor. Okay. All right, I think I'll just end here. So the main message is when you approach here, the valid paramagnon suppress superconductivity. On the majority of phase diagram, you should have sublattice because the system is on the verge of being sublattice polarization. You would have superconductivity in general, and here you don't have superconductivity because simply maybe because the density of state is small. Okay, thank you so much.
Couple questions.
Yeah, thanks for the talk. So your proposal is that the superconductivity has spin triplet uniform spin polarized pairing. Now, the spin triplet valuing superconductor on general grounds, its critical current will be 0. Now, in the experiments, people see a very sharp critical current. So I'm not sure how you reconcile this proposal with lots of data.
So if you have certain amount of spin orbit, the critical current, you say critical current is 0 because you can form phases. Is that what you meant?
The spin orbit is weak, and you can estimate.
Yeah, so that's a numbers game. You have to estimate spin orbit and the system size, and yeah.
The data is very unambiguous. Like the IV curves have a very sharp and big critical current.
Sorry, I don't get the question. The question is.
No, in the data, there is a very sharp threshold where there's a clear critical current.
Yes.
So system size doesn't, different devices all have good shock thresholds.
Yeah, so I was saying if you have spin orbit,
Yeah,
even though it's very small, you have to sum over a critical, select a given size. Let's say, I don't know, half a micron of spin orbit is enough to stop you from having phase leaps. We can talk about that more later. Yeah.
Yeah, I was wondering where your theory can be applied in the whole phase diagram from -4 to +4.
Yes. It might seem like I planted this question, but no. So my theory is mainly around -2 to -3. So this is in absolute electron density, but you can imagine this is around -2 and -3. But there's also evidence of superconductivity around here, okay? And so if my theory is only for a spin projected Hilbert space. So you could use the equal spin pairing mechanism to say exactly the same thing happens in orbital spin, and you move to this filling factor, okay? And the reason why this is slightly smaller is probably because the density of states here is smaller because it's closer to the Dirac point. Yeah.
But the other question is, can you comment on the C2Z symmetry in your theory?
The C2T?
C2Z symmetry.
C2Z, yeah. So if you aligned sublattice, it is an experimental fact. Till today, it seemed like aligned BN MATBG doesn't have any superconductivity. And this is one of the main reasons why we came out with theory, because if you align it, you basically kill any sublattice fluctuations. So you can never go to this part of the phase diagram if you align your boron nitride. Yeah.
Okay, maybe with this, I think we could again move on to one.